Zoax.net. Lesson 12. Optimal Comparison Sort. A comparison is an operation that compares two elements and determines whether or not the elements satisfy the given order relationship. The typical comparison operations are less than and greater than. With a comparison, we take two elements like 85 and 179 and apply a comparison operation like less than to determine whether 85 is less than 179. In this case, the operation will report that the relationship is true. On the other hand, when our less than operation is applied to two other numbers like 64 and 20, the operation will report that the relationship is false. In a sorting algorithm, the comparison is applied repeatedly to different pairs of elements, and the elements are swapped until the entire set is sorted, as we have seen in the prior sorting algorithms. Almost all of the sorting algorithms that are commonly used are comparison sorts that operate this way. Before we consider the optimal sorting algorithm, we will look at the simpler case of an optimized comparison search on a sorted array. Consider this array of sorted elements with the less than comparison operator. Suppose that we are searching this array of 16 elements for the value 57. At the start, 57 could be anywhere. We will illustrate the viable entries by making them white and changing the back after we have eliminated them as possibilities. To start, we compare 57 to the element just above the middle, 45. Since 57 is not less than 45, the comparison returns false, and we know that the value can only be in the last half of the array. Next, we compare 57 to 68 and see that it is less. Therefore, the value 57 can only be in the first half of the remaining entries. 4 viable entries remain. Next, we compare our 57 to the 57 in the array. Since 57 is not less than 57, we know that our value is in the second half of the remaining entries. Next, we compare our 57 to 64. Since it is less than it, we can eliminate that entry and we are left with the remaining entry that contains 57. As we see, we needed 4 comparisons to get down to one element. Each comparison can be either true or false and allows us to eliminate half of the entries in our search. So the number of required comparisons for the search algorithm is log base 2 of the size of the array. Of course, the size of the array will not usually be a power of 2, in which case the number of comparisons required is the ceiling of log base 2 of the size of the array. In any case, the time complexity is big O of log of n, and it isn't difficult to come up with a constant bound to satisfy the definition. Anything larger than 1 will work. For a sorting algorithm, we have n factorial possible arrangements for the elements of an array of size n. Every arrangement of entries can be considered equivalent to a permutation of the numbers 1 through n, where 1 corresponds to the smallest element and n corresponds to the largest element. For example, 94, 38, 24, 47 corresponds to 4, 2, 1, 3. For our purposes, we can assume that the elements that we are sorting are all unique, since multiplicities only serve to reduce the number of possible arrangements. We know that various comparison sort algorithms, like merge sort and heap sort, have time complexity big O of n log n. Given that, it is reasonable to ask, is that the best that we can do? Theoretically, we can divide the set of n factorial arrangements in half after each comparison. For example, there are 6 possible permutations of 3 elements. If we compare the first 2 elements in a set of 3 with the less than operator, we will either eliminate the 3 possibilities on the left or the 3 on the right. Eventually, we will narrow the possible permutations down to 1. That is the equivalent of sorting the array. Given that we have n factorial possible arrangements in an array of size n, and if we can eliminate half of them at every comparison, we can sort an array of n elements with the ceiling of log base 2 of n factorial steps, just as we did for the search algorithm that we demonstrated previously. Can we achieve this bound in practice always? Can we always eliminate half the possibilities? That is a difficult question and not one that I will address. However, I will demonstrate how it can be achieved for an array of size 4. Even though we do not know whether the optimal number of comparisons can be used to sort an array of size n, it is possible to show that the ceiling of log base 2 of n factorial is in fact big omega of n log n, and that therefore is the best that we can do. Recall the definition of big omega. To demonstrate the time complexity, we need to find the constant c and integer n sub 0 that satisfy the definition as shown for these functions. Specifically, we need to find c and n sub 0 that fulfill this requirement. Before we begin, we note that all our logarithms are base 2, so we will not bother to write the base. To start, the ceiling function can only increase the value of the log of n factorial, so removing the ceiling can only reduce the value. Next, we can use the property of logarithms that says that the log of a times b is equal to the log of a plus the log of b to write out the log of n factorial as a sum of the log of its factors. Then we can truncate this sum at the ceiling of n divided by 2, and for the next inequality we can replace all the larger terms by the ceiling of n divided by 2. Collecting these terms together, we have at least the ceiling of n divided by 2 of them. We have one more if n is even. After this, we can take off the ceiling, which can only reduce the value further. To this we can apply the law of logarithms that says that the log of a divided by b is the log of a minus the log of b. So we have n divided by 2 times the log of n minus the log of 2. Of course, the log of 2 is just 1 since our base is 2. Distributing the n divided by 2 term gives us this. Finally, we break apart the n divided by 2 into n divided by 4 and n divided by 4 times the log of n, and group one of them with the n divided by 2 term. Why we did that is not obvious, but it will hopefully become clear as we go through the explanation. For large values of n divided by 4 times log of n dominates n over 2. In fact, for n greater than or equal to 4, this term in the parentheses is greater than or equal to 0. This means that the whole thing is greater than or equal to n divided by 4 times the log of n for n greater than n sub 0 equal 4. Now we see that this fulfills the condition of having our original function in big omega of n log n. Recall the definition of big omega. What this tells us is that the best time complexity that we can achieve for a comparison sorting algorithm is n log n. This time complexity is achieved for merge sort, heap sort, and some others. However, these algorithms generally do not perform the optimal number of comparison steps. Now that we know the best time complexity is n log n, I will show how an optimal sorting algorithm with the absolute minimum comparisons could work. In order to make the algorithm understandable, I will restrict the sort to an array of 4 elements. With 4 elements, we have 4 factorial equals 24 possible permutations. In this case, we can sort the array with at most the ceiling of log base 2 of 24, or 5 comparisons. Here we have a decision tree that we will use in our idealized sort. I will explain it as we go through the sort. Let us begin with an array that we wish to sort. 9, 54, 36, 23, which we note corresponds to the permutation 1, 4, 3, 2, since 9 is the smallest and 54 is the largest element. Now we already know what the final permutation will be by inspection. However, we will go through the idealized sort to show how we would find the permutation via an idealized sort. We start at the root node of the tree, which tells us which two entries to compare at each stage by marking them black. Since the first two entries are black, we compare those. We compare 9 to 54 and see that it satisfies the less than relationship. Since it satisfies the less than relationship, we move to the left child. The left child tells us to compare the last two entries next, 36 and 23. We see that 36 is not less than 23, so we move to the right child node. We have now done two comparisons, and we are on the third level of the tree. This node tells us to compare the first and last entries, 9 and 23. Since 9 is less than 23, we go to the left child again. At the left child, we see that the second and third entries are black. This indicates that we should compare the middle entries, 54 and 36. Since 54 is not less than 36, we move on to the right child. The right child is a leaf node, and we have arrived at it in only 4 comparisons. Most branches require 5 comparisons. So what does the leaf node tell us? It tells us the permutation of the entries, how the entries are ordered. The entries are numbered 1 through 4. So this permutation tells us that the smallest entry is first, then the largest entry is next, the third entry is the second largest, and finally, the third largest or second smallest entry is last. With the permutation 1, 4, 3, 2 representing the array that we want to sort, we only need to apply the inverse permutation to sort the array. This permutation array is its own inverse. So we apply this permutation, which has the effect of swapping the second and fourth entries. This finishes our optimal sort. There is no algorithm for creating this optimal sort in general, and it is probably difficult, if not impossible, to do so.